Hello, and welcome to today's ACM Learning webinar. This webcast is part of ACM's commitment to lifelong learning and professional development, serving a global membership of computing professionals and students. I'm Carol Willing, a research software engineer at Cal Poly San Luis Obispo, working full-time on Project Jupyter. Along with other leaders of Project Jupyter, I'm a winner of the 2017 ACM Software System Award. I'm also a Python Software Foundation Fellow and former director, a Project Jupyter Steering Council member, and a core developer on Python and Jupyter. For more on my background, check out the bio window on your screen. For those of you who may be unfamiliar with ACM or what it has to offer, here is more information. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. Our members can stay competitive in the constantly changing world of computing with a range of ACM Learning Center resources at learning.acm.org. You can see some of the highlights on your screen. Before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. First, the slides will advance automatically throughout the event. On the bottom panel, you will find a number of additional widgets and resources. If you are experiencing problems with the slides or audio, press the F5 key in Windows, Command R if you're on a Mac, or refresh your browser on a mobile device. Or you can close and relaunch the presentation. To control volume, adjust the master volume on your computer. If you have questions during this webinar, please type them in the Q&A box at any time during the webinar and click the Submit button. I'll organize the questions as Brian speaks, and he'll reserve time at the end of the presentation to address them. This session is recorded and will be archived. You will receive an automatic email notification when it becomes available, and check learning.acm.org for updates on this and other upcoming webcasts. At the end of the presentation, you'll see a survey open on your screen. Please take a moment to fill it in to help us improve our webinars. You may also open the link to the survey at any time from the resources window on your screen. You can use Facebook and Twitter widgets on the bottom panel to share the presentation link with your friends, as well as tweet comments and questions using the hashtag #ACMLearning. We'll be watching for your tweets. We also have a new community discourse page to continue the discussions after this webcast, including questions we won't be able to get through during the Q&A session. Today's presentation is Project Jupyter, From Computational Notebooks to Large-Scale Data Science with Sensitive Data by Brian Granger. Brian Granger is an associate professor of physics and data science at Cal Poly State University in San Luis Obispo, California. His research focuses on building open source tools for interactive computing, data science, and data visualization. Brian is a leader of the IPython project, co-founder of Project Jupyter, co-founder of the Altair project for statistical visualization, and an active contributor to a number of other open source projects focused on data science and Python. He is an advisory board member of NumFocus and a faculty fellow of the Cal Poly Center for Innovation and Entrepreneurship. Along with other leaders of Project Jupyter, he is a winner of the 2017 ACM Software System Award. Brian, without further ado, take it away.
Thanks, Carol, so much for the introduction, and also to Jan for organizing everything. And welcome to everyone. I'm going to turn on my screen sharing here and switch over to my presentation, and we can get started. All right, so I'm going to leave the title slide up here for a few seconds. Sometimes it takes a little bit for the screen sharing to go live. It's great to be here talking to everyone today. Also, if you'd like to follow up about anything that I talk about today, my username on Twitter and GitHub is EllisonBG, and would love to continue the conversation after this as well. So today I'm going to be talking about Project Jupyter and the work our community has been doing on Jupyter Notebooks and beyond. And An outline of the talk today. First, I'm going to give an overview of Project Jupyter and computational notebooks and how we think about interactive computing with these notebooks and how Jupyter is being used. And then I'm going to switch over and start to talk about some of the new challenges that we see emerging with the usage of Jupyter for data science and computational research in large, complex organizations. And in particular, how JupyterLab and JupyterHub are helping us to tackle those challenges. So what is Jupyter? Project Jupyter exists to develop open source software, open standards, and services for interactive and reproducible computing. So everything, all the software that Jupyter writes is open source. The license we use is the modified BSD license, and everything is developed in the open on GitHub. And the main thing that Jupyter has become well known for is the Jupyter Notebook. And Project Jupyter started in 2014 as a spin-off of IPython. Originally, IPython was focused on interactive computing in the Python programming language. I'll talk more about how that's evolved over time. And really, the flagship application that we've built is the Jupyter Notebook. And this is an exploratory, interactive, browser-based computing environment for data science, scientific computing, machine learning, AI. And in the slide that I'm showing here to the right, there's a screen. The way to think about what a notebook is it's a document. So you can think of something like Word or Excel the dogs are going to bark here. That includes live code, narrative text, equations in LaTeX, images, visualizations, and audio. And so this is both an environment to write code, but also to share the code and its outputs with other people. And the way that we're thinking about this is the term computational narrative. So it's a narrative or a story around the code and the data that allows you to share that with other people for a wide range of different purposes. And as we started to build the IPython notebook starting in 2011, we quickly realized that pretty much everything we were doing would also work in other programming languages. So in 2014, we created Project Jupyter as a new home for the language-independent parts of the architecture. IPython continues today to be the Python plugin for Jupyter, if you want to refer to it that way. So today there's over 100 different programming languages supported. Jupyter is a fairly large open source project. We have over 500 contributors across hundreds of different GitHub repositories. And so before I move on, I've given a little introduction. I want to address the question of attribution, or in other words, answer the question, who exactly builds Jupyter? And in the slide that I'm showing here, I'm listing the members of the Jupyter Steering Council, which is the governing body for Project Jupyter. All the members of the Steering Council have made substantial long-term contributions to the project. It's important to note that those contributions can vary widely. Many people do write code, but there's there's also people who provide organizational or community or design-based contributions as well. A number of the other core Jupyter contributors are listed here, and I want to emphasize that there are hundreds of other people not listed here. We have dozens of interns over the years at Cal Poly, where I'm at, and then funding from the Sloan, Moore, Helmsley, and Schmidt Foundations. Should also mention that we are a part of the NumFocus nonprofit organization that is an umbrella organization for Jupyter and other open source projects in this ecosystem. And what's the right narrative around attribution? And I think the sort of popular narrative about open source is that attribution sort of works like this, that there's the heroic work of one or two or a small number of people, and I want to explicitly state that Jupyter is not the heroic work of one person, myself, or any other few people. That narrative doesn't fit. And so when you're thinking about the list here that I'm giving, please don't try to wedge it into this type of narrative. Instead, it's more like this, where there's a large number of people with different strengths working in diverse teams to build the software of Jupyter. And I think that's a really important point. So onwards. Jupyter now has millions of users, and it is a very diverse international community. So the table that I'm showing here shows the Google Analytics traffic for Jupyter.org. This table is from September 2017. I checked recently, and as of this summer, Asia is now the most represented continent in Jupyter's web traffic. And so it's a very international audience, and that's something that we're paying a lot of attention to. These computational notebooks that enable people to tell stories around code and data are being shared. And one of the ways that people share those notebooks are on GitHub. And so we have a project shown in the lower right there where we're tracking the overall number of notebooks on GitHub. And as of this summer, there's over 2.5 million public notebooks on GitHub. GitHub also is tracking the trending notebooks. And so in the upper left corner there, you can see some of the popular repositories that have Jupyter notebooks and a link to the GitHub page with the trending notebooks. Right now, obviously, machine learning and AI is very popular. And so the trending notebooks page on GitHub really is a great way of finding good content in that space. One of the patterns that we've been seeing over the last 1 or 2 years is a shift in the usage of Jupyter from ad hoc usage by individuals in organizations to official organizational adoption. And some of this has been driven by JupyterHub, which is Project Jupyter's project to host or deploy Jupyter in large organizations. But obviously, another part of this is that organizations of all types are rapidly becoming aware of the value of data. So there's some of the companies that are using Jupyter here. Jupyter is being used for commercial data science platforms at a number of different companies. It's being used for data journalism, publishing, both in the form of books, but also non-traditional media, such as blog posts, academic papers. It's being used extensively in both K-12 and university education, both in the data space, but also in the broader science and STEM space. It is one of the go-to tools of data science teams in industry, and it's also being used extensively in large-scale scientific collaborations, and I'll talk about a few of those later. One of the things that's fun about working on Project Jupyter is that our users are doing amazing things. And so I want to highlight a few of those things here. The first in the upper left is the LIGO Open Science Center. So the LIGO and Virgo collaborations won the 2017 Nobel Prize in Physics for their observation of gravitational waves. And accompanying all their papers that they publish in peer-reviewed journals, they post Jupyter notebooks on the Open Science Center that allows anyone in the world to reproduce the analysis for those papers. That goes all the way from the original raw data to the final publication ready visualizations. So this is a broad pattern that we're seeing, not just in physics. Here's an example also of a Nature Genetics article that is accompanied by a number of notebooks that reproduce their analysis, and those notebooks are hosted on GitHub. As I mentioned before, Jupyter is being used extensively in data journalism. And the Chicago Tribune, there's a link or a screenshot here of an article they wrote that was a finalist for a Pulitzer Prize, where the consumer-oriented news article was accompanied by an additional post that was automatically generated from a Jupyter Notebook that had all of their data analysis. Gene pattern and LSST are examples of two scientific collaborations in the bioinformatics and astronomy spaces. And then there's an example of a book here, Python Data Science Handbook from Jake Vanderplas. So it's a physical O'Reilly book that you can buy from Amazon or a physical bookstore. And along with that, all the code for the entire book is available on GitHub as Jupyter Notebooks. And so I want to give a little bit of an example about what we mean by Jupyter's being used by large-scale scientific collaborations, and in particular focus on LSST. So this is a new telescope that's being built. It will have a 27-foot primary mirror, a 10-year operating period. I think it goes live in the next few years. Each image covers around 40 moons worth of the sky. So this is a very large-scale survey telescope. And when it's operational, it will produce 15 terabytes of data every single night. And so this is a massive amount of data around, over its lifetime, 3 petabytes of relational database, 4 petabytes of flat files. And you can imagine that every astronomer on the planet will want to work with this data, but it's simply impossible for these astronomers to all download or even subsets of the data. And so LSST has adopted JupyterHub and JupyterLab as basically a cloud-based computational platform for working with their data and doing their computational research with it. Their user base will essentially be every astronomer on the planet, which I hear is around 7,500 people. It will enable next-to-the-data analysis. They'll have scalable compute of over 2,000 cores, interactive analysis, modeling, simulation, visualization, and also collaboration. And so that's sort of what we're thinking about when we're imagining large-scale data science. And one thing I want to mention about large-scale data science that is important as we think about this is that when we think about large scale, we're not just thinking about the amount of RAM or CPU cores, but also the complexity and size of the organizations that are deploying and using Jupyter. And I'll talk more about that. So I mentioned before the open standards for interactive computing. And so Jupyter is really founded on these open standards. So what are they? The first is the Jupyter Notebook format. This is a JSON-based document format for these notebook files. So if you look at the file system of someone working with the Jupyter Notebook, you're going to see these .ipynb files. These files, very importantly, are independent of both the user interface and the programming language. Next open standard is the Jupyter message specification. This is a JSON-based network protocol for interactive computing that allows user interfaces, which are typically web-based, such as the Jupyter Notebook, to talk to kernels that run code interactively in a given programming language. Here I'm using the word kernel not in the sense of the Linux kernel, but more along the lines of how Mathematica has used that phrase. It's basically a separate process that runs on a server to run code in a particular language. And then there's a transport layer for these JSON packets, either over 0MQ or WebSockets. And then the final open standard for interactive computing is the Jupyter Notebook server. And this is an HTTP server that offers a set of WebSocket and HTTP APIs for remote access to the building blocks of interactive computing. And so what are those building blocks? So they're a file system, terminal, kernels. And a point that I want to make here is that the reality of modern cloud architectures and large amounts of data essentially dictates that where the user is sitting is not where their data and their code is. And so they may be on their laptop at their university or at Starbucks or at their company, but the code and the data is going to be sitting somewhere else. What this means is that the fundamental building blocks that you need to work with code and data interactively need to have remote abstractions. And so we've written REST and WebSocket APIs that allow and expose the abstractions of file systems, terminals or shells, and then kernels to a remote process. What are the open source software that we've built on top of these open standards? First is the Jupyter Notebook that was originally the IPython notebook. This includes the notebook server and the web-based user interface that I've shown. JupyterLab, I'll be demoing this today. This is the next generation user interface for Jupyter Notebooks. JupyterHub, as I've mentioned, enables organizations to deploy Jupyter in a scalable, secure, and maintainable manner. IPython continues to exist today as the Python-based kernel for Jupyter. And Jupyter widgets are interactive user interfaces within Jupyter Notebooks. And I'll show a demo of those later on. And NBConvert is a command line tool that enables you to convert notebooks to other formats. I should also emphasize that there are many other projects that are part of Jupyter that I'm not mentioning here, and there's a few others that I will mention in the talk. It's a large project, and there's a lot going on. So these open standards and our open source software provides a set of building blocks that can be used to build a wide range of interactive computing system. And if you want to think about it this way, it's sort of like Lego for interactive computing. And we ship directions for a standard set that you can build with these tools and standards, but you may need to build other things using these standards. And I want to give you some examples now of different ways that we and other people have assembled these things. First is JupyterLab. So JupyterLab is a new web-based user interface for Jupyter. Eventually, this will replace the classic Jupyter Notebook. And the important point here is JupyterLab uses the same notebook format, server, and network protocols as the classic notebook. So all we're doing here is swapping out a different user interface and reusing everything else the same. So notebooks that are created with JupyterLab will run fine in any other user interface that knows how to work with that notebook format. Another example is Interact. Interact is an alternative user interface for working with Jupyter Notebooks with a particular focus on simplicity. It is also open source and is sponsored by Netflix. It's also part of the NumFocus Foundation. And importantly, it uses, again, the same notebook document format, server, and network protocols. Interact has both a desktop application that's an Electron app and a web-based front end as well. Google Collaboratory. This is another user interface for working with Jupyter Notebooks. This one is produced by Google. It's not open source, but it's fully integrated with Google Drive. So all of the same experience that you get with Google Docs and Google Sheets also works, including real-time collaboration, commenting, and so on. And again, it uses the same notebook format and network protocols underneath the hood. Another example is a project from the core contributors of Jupyter called Binder. And actually, Carol Willing, who introduced me, is one of the lead developers of Binder. And the idea of Binder is that a lot of our users are sharing notebooks on GitHub, and they want people to not only be able to view those notebooks, but also run them with all the dependencies required. And that is exactly what Binder does. So on the left, I'm showing a screenshot of the Binder website. You can enter the GitHub org and repo to any repo on GitHub. And what Binder does is it automatically bundles the requirements for running the Jupyter Notebook or JupyterLab or Interact or even RStudio, along with all the dependencies for that and the notebooks in the repository, and exposes that with a single button that anyone in the world can click. So here on the right is the Launch Binder button on the JupyterLab Demo repository. Anyone who visits that repo can click that, and behind the scenes, we instantly spin up a container that's running with all the dependencies that users can explore and run those notebooks. And again, I want to emphasize the commonality in Binder with the underlying protocols and open source tools. Binder is yet another way of assembling these things. At this point, I want to talk a bit about some of the challenges that we're seeing in data science in large, complex organizations. First is human-centered design. If you don't design for humans, you'll design for computers, and humans will be pretty miserable. Some examples. First, the primary user interface for working on a remote computer is still SSH. SSH is a necessary tool for many of us, but from a user experience perspective, when it's the only and primary user interface, that's really miserable. Another example is tracebacks. So tracebacks are still used by most programming languages to communicate to users when a program raises an exception. The idea of an exception and its formatting as a traceback is entirely a design that's driven by how computers represent data in programming languages. If you've ever taught programming, you will know that trying to explain to people that they're supposed to look at the tracebacks and understand how they need to modify the code to get it work is a really difficult ask. Even simple things like you should probably look at the bottom of the traceback first, not the top, are a miserable user experience that comes from designs that are driven and focused on computers rather than humans. You also see Alan Cooper's The Inmates Are Running the Asylum for many more examples along these lines. And I want to emphasize that scientific computing and data science are human-centered activities by definition that involve iterative exploration, analytical reasoning, visualization, mathematical abstraction, model building, moral ethical reasoning, and decision-making. And because of this, we can't afford to not include human-centered design as we think about interactive computing. And in particular, in large organizations, there are a diverse range of individuals working with code and data. Data scientists, data engineers, analysts, marketing, sales, product managers, university administrators, teachers, statisticians, etc. And an important point is that all of these people need to look at in some way and make decisions based on data, but most of them don't want to look at code sometimes or even ever. And this is, I think, a really important point that we're thinking a lot about in terms of what we're doing now and looking forward. In large organizations, collaboration is also essential. Large organizations have complex human networks of people that need to work together, both within and outside of the organizations. These organizations and the individuals have different skill sets, responsibilities, access permissions, roles, work priorities. And again, yet everyone needs to look at and make decisions based on the same overall data. And I want to emphasize something important here, that GitHub is an effective collaboration tool only for people that live and breathe code all the time. For most of the roles and personas that need to make decisions based on data, using GitHub is a no-go. And I think that's a really important thing to keep in mind when thinking about collaboration with code and data. And then also, data sets are often sensitive and confidential. The development of data science and machine learning have largely been driven by open source software and freely available open public data sets. And I think this is a huge advantage. There's other contexts where open data sets make a lot of sense, in particular around scientific research. At the same time, once you start working in large, complex organizations, you realize that most data sets of value are sensitive and confidential and require differing levels of protection. And there's a lot of different ways that data can be considered sensitive and confidential. I'm listing some of the legal compliance frameworks in different jurisdictions here. Of particular note is GDPR, which is misspelled here as GDPA, which recently came into effect in the EU, and then also the California Consumer Privacy Act, which was recently passed. It is similar to GDPR, a Consumer Data Protection Act that will come into effect in California in the coming years. But there's also non-legal reasons why data is sensitive and confidential. It could be as simple as that it's proprietary, that a company has data that they want to keep to themselves for intellectual property and competitive reasons. One way that we're starting to think about data science with sensitive and confidential data is the 5 safes framework. And there's a link to this framework here. And it's described as a framework for designing, describing, and evaluating access systems for data used by data providers, data users, and regulators. And the 5 safes are safe projects, safe people, safe data, safe settings, and safe outputs. And one thing that is really important to mention here is that open source tools can't afford to take a not our problem attitude. This hit close to home for us on Project Jupyter in the last few years, in that Jupyter and other open source tools were certainly used by Cambridge Analytica, SCL Elections, and others to build models with Facebook user profiles for the 2016 US elections. Still to this day, there are GitHub repositories from some of these organizations that contain Jupyter notebooks related to the work they did. And we are troubled by this. And so we are paying very close attention to questions around how open source tools are used, who uses them, and also what can we do to encourage ethical and responsible and even legal, hopefully, usages of these tools. And so this is a really important thing for us and other open source projects to consider. So how are we tackling these things? First is JupyterLab. JupyterLab, again, is a next generation user interface for Project Jupyter. Full supports for the Jupyter notebooks. Also includes other building blocks needed for interactive computing. One of the big design goals of JupyterLab was extensibility. So we have a lot of organizations that are wanting to extend and embed the different components that we're building into other environments. And so in JupyterLab, everything is based on extensions, and anyone can create their own extensions and add them to JupyterLab. We're offering strong integration between the different components, rich handling of different data types. And I should mention that JupyterLab is now out of beta and ready for use. So if you're interested in downloading JupyterLab, see the link here. And one thing that is worth mentioning from the collaboration perspective is that for the last year and a half, we've been working on a real-time collaboration system for JupyterLab that will enable multiple people to open up JupyterLab and to edit and comment on documents in real time. So this includes Jupyter Notebook files, but also source code files. So it will open the door for real-time collaboration of coding, data science, and machine learning. So at this point, I'm going to switch over to JupyterLab and start to demo JupyterLab. And I'm hoping everyone here can see JupyterLab. So I'm running JupyterLab on my laptop. It is a web application, but it's still accessing through the network, in this case, the localhost network, files on my local file system. So in the left panel here, you can see the file system. If I were to click on this home icon, it just takes me to my home directory here on my Mac. So I can browse the file system, see different file types. And so one of the first things I want to point out is the different building blocks for interactive computing. And the first is the file system, right? I need to be able to access files that are on a remote computer. Next is, let's look at those files. So if I go into here to notebooks, actually I want to go over demo files, data, goodness, I apologize. Where did I put these things? Slides, demo. Okay. I apologize. Things are not in the places that I left them 5 minutes ago. There we go. Pandas. So here's an example of a Jupyter Notebook. This notebook here comes from Jake Vanderplas's Python for Data Science Handbook. Again, for those of you who are not familiar with Jupyter Notebooks, a Jupyter Notebook can contain narrative text in Markdown, and you can also include equations through LaTeX. You can include code in any of the different programming languages that the community has built kernels for. Here I'm running a Python 3 kernel, and then rich output. So here's a Pandas data frame, and when we look at that, it comes back nicely formatted as a table. So here's a Jupyter Notebook file. Another building block needed for interactive computing is a terminal. Even though I sort of was a bit harsh on terminals as the only way to interact with a remote computer, nonetheless, they remain extremely valuable when working with remote computers. So here I'm in a web browser. I've got access to a full-blown terminal. I can run anything that I would want to do through a terminal through this. Another building block that you need for interactive computing is source code files. So here's a Python file that has some code that will solve the Lorenz differential equation, one of the early differential equations that exhibits nonlinear chaotic behavior. So in JupyterLab, I can open this file with syntax highlighting, tab completion, and so on, and work on this here. I want to emphasize that even though JupyterLab looks a lot like a traditional IDE, there's some important differences. So first of all, we have a web-first design that enables us to run on remote computers. And for organizations working with large amounts of data, this is critically important. Traditional IDEs are fantastic for doing software engineering, but most of them do not have a great experience for installing on remote computers. And so a web-first approach that we've taken in Jupyter and in JupyterLab is really important. Another important point is the sort of reality of interactive computing. And so Jupyter remains focused on working with code and data in interactive ways where there's a human in the loop, running code, writing code, looking at the output, and then iterating in that process. Another one of the building blocks that we have is the idea of a console. So here's the different kernels that I have installed here. So I can open up a Python 3 console and do import math.tab, and start writing code interactively. This is, if you've ever used the traditional interactive shell of Python or the command line version of IPython, this is a very similar experience here with full support for the rich output of Jupyter. And what I want to do now is start to show you some of the ways that we're starting to think about working with data in ways that involve more direct modes of interaction. So obviously, Jupyter's bread and butter is working with code and data by writing code directly. But as I mentioned before, there's many people who need to work with code and data that don't want to look at the code all the time. And so what we've done in JupyterLab is to make an extensible way of loading data into JupyterLab. And let me just show you how this works. So here's a GeoJSON file. And if I double click on it, I'm going to see a collapsed tree view of the JSON data. However, if I right click on it, I can select Open with GeoJSON. And here we've created an extension for JupyterLab that knows how to render GeoJSON files using the leaflet JavaScript library. And again, this allows a more direct mode of interacting with the data that doesn't require an individual to actually install and import some Python library for working with this data. Obviously, you can still do that, but many times you simply want to look at it. Here's another GeoJSON file that we can open. This has the museums in Washington, D.C. Different map tile sets are supported. At a conference about a year ago, to emphasize the extensible nature of JupyterLab, there was a grad student working in bioinformatics, and one of the data formats that they work with is called FASTA. And this graduate student sat down and wrote a JupyterLab renderer for FASTA files. And so here's a FASTA file in JupyterLab, and I can just double click on it, and this renderer I have installed, and that data will immediately be rendered, although it looks like there's some sort of unhappy sad face icon there, and I'm not sure what that is. And so, again, the goal here is for us to expose different ways for interacting with data that go beyond just the writing of code. Another file format, obviously, you can double click on images, and those will open. Here is a Vega Lite file. So Vega Lite is a declarative statistical visualization format, and the file is rendered immediately. And I can also right-click here and open this in the text editor, and I can rearrange the files like this. Here you can see the JSON data of this file, and I can actually go in here and change the mark type to a bar chart, and the visualization will automatically update. So one of the things we've done in JupyterLab is to think very carefully about different models and views attached to a given type of data. And so what's going on here in JupyterLab is there's a single model for this data, and then the two panels that I have open are two different views. On the right, I have an actual editor for the JSON data, and on the left, I have a live rendering version of that. And anytime the underlying model changes, both views will automatically update. One of the important things about this model is that this works for all file formats. This is not something that we did specially for Vega Lite files. So here's a Markdown file. I can right-click and say Show Markdown Preview. Here I have a Markdown preview. If I start to edit this, let's add more text. If I stop typing for a second, the Markdown preview gets automatically updated. There's a delay there because we found that if we update on every keystroke, the rendered Markdown looks very jittery. To emphasize the interactive nature and goals of JupyterLab, what I want to do now, so this Markdown file has some Python code. It would be nice if we could run that. So I'm going to create console for editor. And here is a code console using the Python 3 kernel. And I can select a line of Python code and hit Shift-Enter, and that code gets sent to the console. And here I can put my cursor in a triple backtick fenced block of Python code, and then hit Shift-Enter. It will detect that block of Markdown or that code in the Markdown and run it. You can see the data frame here. And here is a visualization of the data frame using Matplotlib. And again, this is the type of interactive, direct manipulation type of workflows that we're thinking about with JupyterLab. So one more thing to show here to emphasize the language-independent nature of this is I want to open up here a notebook. So this notebook here is using a C++ kernel. So this is a C++ kernel using the leaflet library for creating interactive maps in a notebook. So here I'm importing some header files in C++. I'm going to create a map, and it'll pop open here. So here I have, so this is the Jupyter widgets library that I referred to earlier. So I have a leaflet rendered map whose data model is actually sitting on the server in the Python process. And here I can actually write C++ code to add an observer on map.center. And so what you'll notice now, as I move the map around, I'm observing the mouse position and then the center of the map. And so there's two-way binding of code in the Python process and in the views in the front end. We can look at the different map tiles sets that are available. And if I scroll down here, we can actually create and add a tile layer. And if I scroll up, we can see that we've added a weather-related data set. And so again, here I'm running C++ code interactively with data and with, again, this sort of direct manipulation and working with the data. So at this point, I'm going to switch back to my slides and finish up and talk about a little bit about JupyterHub. So JupyterHub, so this is our open source project for scaling Jupyter deployments to multiple users in large organizations. And there's three key abstractions with JupyterHub. The first is the notion of an authenticator. That's an extensible API for identifying and authenticating users. A spawner that's responsible for managing the processes or the servers that run on behalf of the single user. And then a proxy that dynamically maps URLs to single user servers. To give you the sense of what we mean by large organizations, some of the larger deployments are in the many tens of thousands. UC Berkeley recently ran a course through edX that had on the order of 100,000 users using JupyterHub. I know I'm running short on time. Want to mention some of the new work that we're beginning on JupyterHub for sensitive data. The first is what we're calling organizational data models. This is basically users, groups, role-based access systems, resources, and integration with directory services. I think about this as a way of mapping complex organizations into a deployment for interactive computing. The second abstraction that we're working on is the idea of projects. And this is basically a shared workspace for text files, compute, notebooks, that allows multiple people to have both a well-defined scope for collaboration, but also for data access and security. So within a project, there will be very clear semantics about data access and security. Another really important thing when running Jupyter with sensitive data is telemetry and event logging. It's needed for monitoring, auditing, and compliance, as well as operational purposes. And then the last, a lot of the plumbing for working with sensitive data has to do with the realities of deployments. In particular, making them reliable, secure, and maintainable. In a lot of these compliance frameworks, a lot of work goes into establishing security checks and constraints, and then monitoring and running a deployment in a way that validates that those checks and constraints are being followed. So we'll be working on encryption, and then also declarative, immutable, and continuous deployments using Helm and Kubernetes. This particular work on JupyterHub with sensitive data is a collaboration with Julia Lane at NYU and Fernando Perez at Berkeley, and is a new effort being funded by the Sloan and Schmidt Foundations. And with that, I'm going to stop and open it up for questions.
Thank you, Brian. Let's move on to the Q&A. And the first question, actually, there were several that had to do with sharing of notebooks. And the first one is, what is the preferred way to share notebooks with colleagues? And can only the script part be saved, which I'm assuming is just the actual code itself?
Yeah, fantastic. Great question. So I'll answer the second part first. When you save a notebook, it includes both the source code, the narrative text, so all the markdown and LaTeX, as well as all the outputs. So when you share a notebook with someone, if they open it on their computer, even without running any code, they're going to see everything that you did. In terms of popular ways that people are sharing notebooks today, I would say there's different reasons people are sharing. GitHub probably is one of the more popular ways that people are doing this, although I would say that usage case tends to be more on long timescale collaboration and on sharing it with people who want to consume the notebooks, not necessarily work with them and edit them with the original author. Ideally, this is where the real-time collaboration system that we're building for JupyterLab would come in, and that more focuses on short-time collaboration where 2 people or more people are working on a set of notebooks at the same time.
Great, thanks, Brian. Another question we had has to do with sharing notebooks on GitHub, which you mentioned, and the problems when 2 or more people are editing the same notebook. Merge is not easy because the IPYNB files combine the code and data.
Yeah, so this is probably the most reliable question we get in the talks we give about Jupyter. And yes, it is painful. The underlying cause is that Git and most version control systems are line-based, and there's no reason that a line-based version control system will be able to diff and merge JSON-based files in a way that makes any sense at all. There's also the fact that some parts of a notebook change more often, such as prompt numbers, outputs, and you might not want to sort of be dealing with diffing and merging of those things. One project to look at is called NBDime for Notebook Diff and Merge. This is a project that was built by a grad student working with Min Reagan Kelly, or actually I think it's a postdoc, sorry, working with Min Reagan Kelly at Simula Research Labs in Oslo, that provides a set of tools that makes diffing and merging notebooks with Git more pleasant. For example, there's command line based custom Git diff and merge tools that once you install provide a very pleasant command line experience for diffing and merging notebooks. NBDime also has a user interface for working with diffs, and we're currently working on integrating that more closely into JupyterLab. So it definitely is a painful area and something that we and others are working on.
Great. Thank you, Brian. Another question is, the notebook format blurs the distinction between standard output and the value of an expression, as both appear right below the input. Which do you recommend using? How do you handle this with teaching programming? Students get confused about what to write because there's no apparent difference between print foo and foo.
This is a fantastic question. And so one distinction that I make in teaching is between print, which will always, at least in Python, give you the text-based representation of an object, and then the Jupyter display system, which can generate these rich representations. So if you have an image object, the representation of that in the notebook will look like an image. Or when I was showing the nicely formatted table views of pandas, those rich formats are automatically triggered by an expression that's the last expression in a cell, or can be manually triggered by a function that lives in IPython called display. Basically, display works just like print does, but for these rich formats. So that's one distinction that I often make in teaching. And then the other is that I personally try to be as explicit as possible. Now, at the same time, I don't, for example, put an explicit display call at the end of a cell. That's something that I and everyone else has sort of gotten used to, that if you want to display an object in a notebook, just put an expression with that variable name at the end of the notebook. This is something we continue to think about, in particular in how we represent outputs. The Python kernel in particular has special semantics around outputs that are the last expression in a cell, and that you can access them through a special variable in the Python kernel. And we're continuing to think about what the best way of dealing with these things is. Another thing to mention along these lines is a number of people, including some of the Cal Poly interns this summer, have started to play with reactive data flow kernels for Jupyter. Some of you may be familiar with Observable HQ from Mike Bostock, that is a JavaScript-based notebook that has more of a reactive data flow model. And in these types of kernels for Jupyter, you often end up in a situation where the outputs there can only be one per cell, and that output is automatically displayed and updated by the underlying reactive data flow system. So there's a lot of flexibility in Jupyter as a whole, but hopefully this answers the question.
Great. Thank you, Brian. There are many, many questions. One of them is, how do you get involved in contributing to any of the Jupyter projects?
Great question. So we all of our work is done in the open on GitHub, and so there's a lot of different repositories that we have. We realize that the number of repos is probably overwhelming. Some of the projects that are probably good starting points would be JupyterHub for people interested in the large organizational deployment aspects. Binder is another really interesting project right now, really focused around sort of reproducible computational research. For the user interfaces, JupyterLab, we're slowly spinning down development on the classic notebook, but we encourage people to come and work on that as well. And so I would encourage people to sort of pick an area of the project they're interested in, and then come and start to look through issues. We try on GitHub to curate issues that are good issues for people to tackle for first contributions. Another place to go is gitter.im, Gitter.im. This is an online chat system that is closely integrated with GitHub that we use, that all the developers and contributors use to discuss things. And so there are chat rooms on Gitter for a lot of the open source projects that I've mentioned here. And there should be links from the different repositories to those Gitter chat rooms. So feel free to drop by and introduce yourself. We love new contributors.
Great. I'm afraid we've run out of time for today, but I'd like to thank Brian again for his informative presentation and insightful answers to the many questions. And a special thanks to each of you for taking the time to attend and participate today. This webinar was recorded and will be available online in a few days at webinar.acm.org. You can find some announcements on upcoming webinars and other ACM activities at learning.acm.org and at the main site, acm.org. Also, we encourage you to please fill out our quick survey where you can suggest future topics or speakers, which you should see a link on your screen now. On behalf of the ACM, Brian Granger, and myself, Carol Willing, thanks again for joining us, and I hope you will join us again in the future. This concludes the webinar.
Thank you, everyone.